Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 36, Organic Chemistry 1. Today we will continue on chapter 8, Structure, Synthesis and Reactions of Alkenes. Oxidative cleavage of alkenes. Oxidative cleavage using hot concentrated potassium permanganate. In the previous lecture, we have talked about the action of permanganate dilute and cold potassium permanganate on alkenes, and we have mentioned that it gives the glycol 1,2-glycol. In a potassium permanganate dihydroxylation, if the solution however is warm or acidic or too concentrated, oxidative cleavage of the glycol may occur. In effect, the double bond is cleaved to two carbonyl groups. The products are initially ketones and aldehydes. However, aldehydes are oxidized to carboxylic acid under this strong oxidizing condition. Of course, the aldehyde will be carboxylic acid. If the molecule contains a terminal group, CH2, it will oxidize initially into formic acid, which can oxidize further to carbon dioxide and water. Here, potassium permanganate will cleave, give oxygen in here and oxygen here. Ketone, stable. Again, we have tri-substituted alkene. Will break here, form ketone and form aldehyde. Aldehyde will oxidize further to carboxylic acid. Aldehyde will oxidize further to carboxylic acid. Now, if we have terminal alkene, will cleave in here, form ketone. This is stable, and this is formaldehyde. Formaldehyde further to formic acid, and formic acid will oxidize further, depends on the reaction condition, to carbon dioxide and water. Here is some examples. Propylidene cyclohexane will oxidize under the action of potassium permanganate, warm and concentrated potassium permanganate, to give cyclohexanone ketone, stable. And here we have hydrogen, so it will be initially aldehyde and then further to propanoic acid. Let's see what will happen to limonene under the action of concentrated potassium permanganate and heat, warm up. This will carbon will give here ketone, and this has one H, so it will be initially aldehyde and then further to carboxylic acid. Here we are, this is carboxylic acid, and here is the carbonyl. We come to this double bond. This will be ketone, and this one will be formaldehyde, then formic acid, and if we give it longer time, it will be carbon dioxide and water. Ozonolysis. Ozone O3 cleaves double bonds to give ketones and aldehydes. O3 ozone has two resonance structures, and we react with alkane to form primary ozonide, molozonide, which rearrange via ring open, ring closure to more stable ozonide structure with 5-member ring. Open the ring, have a double bond on this oxygen carbon, then cleave, open, form a double bond in here where the oxygen has a positive charge and this oxygen has a negative charge. This oxygen will attack on the carbonyl carbon atom, and the 2 electrons of the biclouds will attack on this carbon. Ozonoid, under the action of mild reducing agent, will break up to form 2 carbonyl species, and the dimethyl sulfide will be dimethyl sulfoxide. If we were using the zinc and water, the zinc will be zinc oxide. To simplify what will happen, here we have the alkene under the influence of ozone followed by reducing agent dimethyl sulfide. What will happen here, we cut the double bond, put them far from each other, and add oxygen to each species. This is a product, okay? And if we are using dimethyl sulfide, will be dimethyl sulfoxide as a byproduct. All right? It's clear, huh? Okay. Now, let's have some examples. Here, this compound E3-methyl hept3-ene under the influence of ozone, then zinc and water. You cut in here, then you give an oxygen in here and the oxygen in here, and the product is butane-2-one and butyraldehyde. If you have limonene, you cleave in here, double bond, and in here. Here will be carbonyl, ketone. This has, carbon has 1 hydrogen, then it is aldehyde. This carbon will be ketone, and this carbon will be formaldehyde. And that's it. So we get 3-acetyl-6-oxoheptanal and formaldehyde as a product. Ozonolysis, reduction of unknown alkene, gives an equimolar mixture of cyclohexane carbaldehyde and butane-2-one. These are the products from the ozonolysis of unknown alkene. Determine the structure of the original alkene. You remember when we had the alkene, we cut it 2 pieces. Now, we will take the 2 carbonyl, put the carbonyl in front of each other, okay? Then eliminate these 2 oxygen and take this bond, these 2 bonds, and fuse them in 1 bond. So the structure is E2-methyl-but 1-enyl 1-yl cyclohexane. This is the structure. Could be this one or the Z isomer. Could be this one or the E isomer. All right? Once again, take the carbonyl, put them in front of each other, take the oxygen out, fuse these bonds to form 1 bond that is a compound. So here, the other isomer, when you draw the structure this way, so Take the oxygen out, fuse them to get the Z structure. Predict the products that are expected when each of the following alkenes is treated with ozone, following by dimethyl sulfide. 1R4R bicyclo 221 hept2ene under the influence of ozone followed by dimethyl sulfide. We cut in here, we add aldehyde in here and carbonyl in here, aldehyde again because this one has hydrogen and this carbon has a hydrogen. If you have E3,4-dimethyl-3-hexene, we cut in here, we add oxygen to this, we add oxygen to that. So the product is butane 2-on, so one molecule of this will give 2 molecules of that. Okay, so we can write that we have only butane 2-on as a product. And if you don't balance it, that's fine. If you balance it, you have to add 2. Identify the structure of starting alkene in each of the following cases. C10H16 upon treatment with ozone followed by dimethyl sulfide to give C5H8O. Here is C10 and here is C5. This means that you have here 2 cyclopentanone. You put the carbonyl facing each other like that. Take this out. Well, fuse these two together to make one bond. This is the starting C10H16 compound. Now to get to the second one, C8H14. Again, treat that with ozone followed by dimethyl sulfide to give octane 2,6-dione, C8 in here, and here is C8 with 2 carbonyl. All what we have to do, redraw the structure of the octane 2,6-dione. So these 2 carbonyl facing each other again. Take the oxygen out, fuse them together to obtain the starting alkene 1-ethyl 2-methyl cyclopent 1-ene is our structure. Olefin metathesis. Metathesis, in the general sense, is the formation of a product that has exchanged bonds between the starting materials. AB plus CD make the exchange to give AD and CB. For the olefin, we call it double replacement displacement reaction. If you have an olefin carrying AA and another one carries BB, we add a catalyst to them, cleave this one into half, and again cleave this into halves, and then recombine this half. We end up with AB in an E form or in a Z form, right? That's what we call it metathesis. We divide the alkene into 2 alkylidene group and then recombine them differently. So when we have propene, Operating at a metathesis methodology, the two molecules of propenes, okay, we cut this in half and this in half, so divided into alkylidine groups, recombine the alkylidine groups, so we either get the trans E-butene or the cis plus the ethene. Here the Schrock molybdenum metathesis catalyst, and here is the ruthenium Grubbs ruthenium metathesis catalyst. With Chauvin, they obtained Nobel Prize in 25 in chemistry. Chauvin proposed, if we start with the transition metal carbene or alkylidine metal with alkene, we get a 4-member ring intermediate. Then we cut again this to form ethylene and a new metal alkylidine. With alkene, again 4-member ring. Unstable, decompose to the product, giving out product, and regenerate the original catalyst one more time. So Chauvin proposed that the metal alkylidine catalyst form an intermediate 4-member ring with alkene. Learning the skills of solving problem. Show how you would synthesize each compound starting with alkene or cycloalkene. You may use any additional reagent you need. How you synthesize the compound? Well, looking for here, we can start from the bromo analog, and the bromo analog we can get it from the cycloalkene. So starting from cyclopentene, treat it with N-bromosuccinimide in presence of light, allylic bromination. This is allyl group, you can see it this way. Now, substitution reaction using cyanide. You substitute the brom with Cn. It's a very simple synthetic approach. How can we synthesize this molecule? Okay, backward again, we can get this piece from the alkene, and this molecule we can get from alkoxide O minus C plus here. This means that you have an alkyl halide, partially positive, partially negative. If you would like to get a charge positive on carbon, we link it to more electronegative element. Well, how we can get the bromine here? We can start from this alkene. Again, here is allyl position, so starting with this molecule, we can get this one. Now, how we can get this oxygen having negative charge from alcohol? We can get the alkoxide by treating alcohol with sodium. Okay, how we can get this? This is OH, and here is carbon has an H. So we can get this from alkene. Starting from this compound, methyl cyclopentene, we would like to add now the OH on the carbon carrying more hydrogen. So you mean it's clear that it is anti-Markovnikov. How we can do that? By treating it with borane first, and second step, treat it with hydrogen peroxide in presence of base. We get the addition of water, anti-Markovnikov. Treat this alcohol with sodium, we can get other alkoxide. Now, starting with this alkene in the bromosuccinimide, we get the molecule B. We add A to B, we get this compound. All what we have to need now is to form cyclopropane on this, so we can just treat this compound with diiodomethane in presence of zinc copper. We get the target molecule plus enantiomer, because you are going to get enantiomer in this step, okay, and that will carry on with you all the way. So you get the compound with its enantiomer. How we can obtain this compound? This compound has 14 carbon. We can start with a compound has 8 carbon. Using metathesis, we cut this to the alkylidine, and then recombine. This will be 7, and this will be 1. 1 plus 1 is 2 ethylene. 7 plus 7 is the ENZ of the C14, the desired compound. Look at this molecule. It is diene with 13 carbon. So we can start with 5. It has 2 here. So we cut this. So this is 5 carbon. 5 carbons with 2 alkylidine is cyclopentene. And we need, it's 5. We need 4 plus 4, 8, plus 5 is 13. So we start with 4, 4, okay, and they are symmetric, so we can get from one compound with 8. When we cut this, will be here is 4 and here is 4, plus a 5 obtained in here. Put them together, we get the desired compound in isomeric form, AZ mixtures. I hope that the topic is clear, and if you have any questions, please write me in your comments. Best wishes. See you in the coming lecture. Bye-bye.